Hi, everyone. Welcome to this mini course on topological four manifolds. My goal in this very short video is to give you an overview of what to expect in this mini course, especially in the recorded talks versus the live talks that are coming up in a couple of weeks, and also to give you a sense of how this mini course fits in with the other two that are taking place in the same summer school. So one of the really fascinating aspects of dimension 4 is that it's the first dimension where we see a difference between the topological and smooth settings. So in particular, there's behavior that can occur topologically, but not smoothly. And so between the three of us, we'll give you plenty of examples of where this happens. And my task, as you may have expected, is to focus on the topological side of things, to tell you what we know in the topological category and what more there is to be done. The central work in the topological category is the work of Friedman and Quinn. So this has two flavors. So let me explain how that works. The first part is it sort of provides the context for smooth results in that it gives you a difference between the topological categories and smooth categories. So as an example, we have a complete classification of closed simply connected four manifolds up to homeomorphism. And this includes, for example, the topological four-dimensional Poincare conjecture. Of course, in the smooth category, the smooth four-dimensional Poincare conjecture is open at the time of this recording, and there's nothing even close to a classification of closed simply connected four manifolds. And so this dichotomy, that's going to be a focus for us, and we're going to, for example, we'll see how we can prove the topological four-dimensional Poincare conjecture. So that's one thread. And the other thread is work of Quinn, which is telling us that in some situations we're able to use tools and techniques that are familiar to us from the smooth setting. So the key central result in this direction, you may say, is that non-compact connected four manifolds are smooth. And in particular, knowing something like that helps us to get these fundamental tools in the topological setting. Things like if you have submanifolds, you can perturb them until they intersect optimally. It's sort of relatively straightforward in the smooth setting, but in the topological setting, we have to do some work to get there. Or for example, if you have a submanifold, when do we know that it has a nice neighborhood? Relatively straightforward for smooth four manifolds, not so easy for topological four manifolds. So that's something we're going to focus on in this course as well. And then finally, in case you're thinking, well, we know a lot in the topological category, that's true. There's still quite a bit that is left to do that we could be thinking about. So in the very last lecture, I'd like to discuss some open problems, and many of these can be accessed using smooth tools. Some of these are purely smooth open problems, and knots and links will show up, all of this stuff. Okay, so that's the overall outline of the course. A quick word on logistics. So there will be typed lecture notes available on the mini course website. In the talks, my focus will be on giving you an idea of how proofs work, not a ton of details, focusing on the bigger picture. The typed lecture notes will have a few more details. They'll have more specific references and so on. So I encourage you to look at them. They may improve over time. There'll be lots of exercises sprinkled in as well. They'll come in three types. There'll be green ones that are relatively friendly. For example, if you're learning about Handel decompositions for the first time in the summer school, then please do work on the green problems. They will help you not just in this course, but also in the two others. If this stuff is somewhat familiar to you already, for example, if you already know about Kirby diagrams and so on, then the orange problems are for you. They will take a little bit of work, but they're still more or less doable. And then there are red problems that are challenge problems. So feel free to skip those, but read the statements. But that's something if you really want to get into this stuff, and then you're really learning all the nitty-gritty details. And then finally, I chose to do the recorded talks as slide talks just because, well, I hope that you will pause and move back and forth as necessary. Watch them at your own speed. The live talks will be Blackboard talks. All right. Then Finally, I wanted to tell you what the goal for the recorded lectures are. So in András's first lecture, you heard about this theorem. This theorem says that if you have smooth, closed, simply connected, oriented four manifolds, and they have isometric intersection forms, then they are in fact homeomorphic. So in the 2 hours that I have for you before the live talks begin, so in these recorded lectures, I will give you how to prove this theorem. This theorem has two parts. The first part is due to Wall, which says that isometric intersection form implies that the manifolds are H cobordant. I'll define that in the next video. And then the second part is work of Friedman that tells you that H cobordant four manifolds are in fact homeomorphic. So coming up in the recorded lectures is the proof of both of these implications, some warm up, and then that's it. So see you in the next one.